In this video I'm going to explain what pressure is. So we'll start with the definition of pressure, which is that when a force is applied, which is perpendicular to the surface area over which it acts, then the pressure is the force divided by the area of application. So we can write that as P equals F over A, where F is the force, which is measured in newtons, A is the area of applications, which will be measured in meters squared, and P is the pressure. So what are the units of pressure then? Well, the equation basically tells us what they are, because we've got newtons divided by meters squared, so we get newtons per meter squared. And that's given its own name. It's called Pascal, which is PA. So the unit of pressure is pascals. So let's apply this formula in an example. So let's do a very simple one. It's just a person standing up, and the mass is 60 kilograms, and each foot has a surface area of 130 centimeters squared. So we're going to look at the person standing on both feet, and the same person standing on just one foot, and then the same person standing on tiptoes. So we're going to need to convert the 130 centimeters squared into meters squared first of all, because in the formula we used the units of meters squared. So 1 centimeter is 10 to the minus 2 meters, which means that 1 centimeter squared has to be 10 to the minus 2 squared meters squared. And 10 to the minus 2 squared is 10 to the minus 4. So every centimeter squared is 10 to the minus 4 meters squared. So now we can put all this in the equation. So we've got that the pressure is force divided by area. So we know that force is equal to mg, and the mass is 60 kilograms, g is 9.81, and then we're going to divide that by the area, which is 130 times 10 to the minus 4. And now we're going to put that in our calculator to get the answer. Oh, and actually, we forgot something here. Did you spot the mistake? We were standing on both feet in this case, which means that we're going to have to double the area. So I'm going to put times 2 here, which means that the answer is going to be 23 kilopascals. So now let's think about what would happen if the same person is standing on just one foot. Well, we actually kind of did that calculation by mistake, because when we put the area of just 1 foot in the equation, then we get the pressure. So we know that the force is still going to be the same, just that the area is now 130 centimeters squared. So on the calculator that showed us earlier that it was 45 kilopascals, and it should be double what we had when we were standing on 2 feet, because the area is half of what it was. So in this case it's not quite double. But that's only because we're rounding it to 2 significant figures. And then the final example, when we're standing on tiptoes, we're going to need to know the area of the part of the foot that we're standing on. And let's say that area is 50 centimeters squared. Then we apply the same formula, so we've got the pressure equals force over area. The force is still exactly the same as it was in the others. But the area has changed to 50 times 10 to the minus 4, and the answer is 120 kilopascals. So you can see that even though the force exerted on the floor is the same in all 3 cases, the pressure is very different. So standing on 2 feet, we're spreading out the force the most. On 1 foot, we're spreading it out a little bit less, so it's slightly higher pressure. But standing on tiptoes, we're concentrating the force on the lower area, so we get a much higher pressure. So let's look at why we can also apply this pressure formula to gases. The reason why we talk about the pressure of a gas is that when gas molecules are flying around in a box, say, they collide with the walls and exert a force, and that force is perpendicular to the wall. So that raises 2 questions. The first one is, why does a gas exert a force on the wall? So let's say we have a wall, and then we have one particle coming in directly towards the wall, so it's flying in perpendicular to the wall. And the momentum it has before, we would just call P before, and the momentum that it has afterwards, we call P after. And because it collides head-on with the wall, the momentum is just reversed. So momentum before is negative, the momentum after. So it's just switched directions. So this means that there's a change in momentum, delta p, which took a time delta t to happen. And remember, Newton's second law can be written as that the force is the rate of change in momentum. So F is delta p over delta t. So in order for this momentum to change, that means that there was a force by the wall on the particle. And by Newton's third law, we then also know that there was a force applied by the particle on the wall. So that's how we know that there is a force exerted by the gas on the wall. But then the second question was, why is the force perpendicular to the wall? Why isn't it in all different directions? So if we have a few particles, they're going to be moving towards the wall in various directions. So let's zoom in on just one of these, the one that's moving diagonally down. So here's its momentum before it hits the wall, and here's its momentum after it's hit the wall. To find out the change in momentum, we have to take the momentum after the collision and subtract the momentum before the collision. And we can do that using vectors. So we've drawn both of these arrows, so we can draw them out. So we're going to do momentum after, and then minus momentum before means that we switch the direction of the momentum before arrow. So we draw it this way. And then the resulting arrow is going to tell us the change in momentum. And you see that the change in momentum was actually perpendicular to the wall. So whichever direction the particle is coming in at, its change in momentum is going to be perpendicular to the wall, which means that the force is perpendicular to the wall. And therefore we can use the pressure formula that we had to say that the pressure is force over area when the force is perpendicular to the area. So let's look at one example of applying this formula to a gas. So say we have a wall with a gas on one side at atmospheric pressure, which is 101 kilopascals, and on the other side we have a vacuum. And there's a wall that separates them, which is 10 centimeters squared. And if we convert that into meters squared, then that would be 10 to the power minus 3. So now if we want to find out the net force on this wall, only the gas is going to be exerting a force, not the vacuum, which means that we only have to consider what's happening on the gas side of the wall. So we know that the force is equal to pressure times area, if we just rearrange the pressure equation. And then we just have to put the numbers in. So our pressure is 101 kilopascals, so it's 101 times 10 to the power of 3. And then the area was 10 to the minus 3. So the 10 to the power of 3 cancels out with the 10 to the minus 3, and we just get 101 newtons. So that's the force exerted on this wall. And that's quite a big force, isn't it? Because 100 newtons is about the size of the force due to gravity of an object with a mass of 10 kilograms. So keeping a vacuum on one side of the wall and a gas on the other side of the wall means that we need a very strong wall that can take the equivalent force of a 10 kilogram mass.